So these are the notes on exponential functions. I'm going to do a briefer version than what's on Schoology because I got limited time. But here they are, and you can take the notes from this. All right, first of all, what is the general shape of an exponential function, and what defines an exponential function? Well, and as usual, it's in the name, the exponent. When the exponent, the power, is a variable, that makes it an exponential function. So not things like x squared, that has an exponent and a variable, but the exponent is a constant here. That's just a quadratic. When you have it reversed, so things like 2 to the power of x, now that's exponential. Now, if we look at what exponential functions look like, just a couple of quick exponent rules. If you raise anything to the power of 0, 2 to the power of 0, x to the power of 0, any number, it could be 10 to the power of 0, that doesn't equal 0. Those all equal 1. It's one of the rules in math, and I can prove it to you with anything. 5 to the power of 0 is 1. So what that means is the y-intercept of an exponential function, kind of by default, is at 1 on the y-axis. So when x is 0, it's at 1. Now this changes, of course, if there's a leading coefficient, but that's just an extra thing that, can be multiplied on the front of any function. So that could shift it or move it up or down. But without getting into too much, because I'm just trying to give you the overall shape, we have a y-intercept that's based off of this property. As you go into higher and higher powers, this is where the key feature of exponential functions come into play, it's going to jump up very rapidly. So, things like, if again we're doing 2, 2 squared is just 4, but 2 cubed would be 8, and 2 to the 4th would be 16, 2 to the 5th jumps up to 32, 2 to the 6th would be 64, after that 128, 512, and then it's 1,000 something. You just keep going higher and higher and higher. So this rises very rapidly, and that's one of its kind of defining features. So I'm just going to roughly sketch that by just a curve that goes up very steeply, and it goes steeper and steeper and steeper the further you go this way. Now, what does it do on the other end? What happens when you have negative powers? And this is where again you have to remember how negative powers work. When you raise something to a negative power, it doesn't equal a negative number. It equals 1 over that number to the positive power. So 2 to the negative 1 is 1 over 2 to the first power of 1 over 2. 2 to the negative 2 would be 1 over 2 squared, which is 1 over 4. So you actually have this descending fraction. It will never actually equal 0. It will just keep going down, 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 but just kind of leveling off, getting a smaller, becoming a smaller and smaller fraction. So this gives us an asymptotic shape, a shape of infinitely approaching 0, but never quite reaching it. And so this is the main shape of our exponential function. There is a horizontal asymptote at y equals 0, and it goes through the y-axis, generally at 1, but again, if there's an a value, then it's going to cross here at whatever the a is. So I'm actually going to label that as a because that's technically true. If there's a 2 there, then it'll cross at 2, but whatever. But this is the main shape. It spikes up like this. By the way, this is, as we read left to right, an exponential function which grows over time. This occurs in examples like I've shown here when the base, or the b, is greater than 1. Has anything greater than 1, by the way. So obviously 2 is greater than 1, but 1.1 would be greater than 1, 1.01 would be greater than 1. It would still have this same basic shape. This other graph is to show you what would happen if the base, not the a can be again whatever, but the base itself was a fraction. So if the base was a number less than 1, but by the way, exponential functions don't work if the base is negative, so it would have to be greater than 0. So this is a fraction. Things like 1/2, 1/3, 3/4, those would all be valid ones. How would the function look if the base was a fraction? Well, all these rules, I won't write them out, would kind of apply almost in reverse because this negative exponent rule. So negative exponents would flip the fraction and get you big, big numbers So you would almost have, you'd exactly have that spike going up, but in the opposite, way. I'm having some lead issue here. So let's use a different pen. But yeah, it would spike up this direction, like that. And then the other direction is it would level off this way. The same thing, you have an asymptote at y equals 0. As you get higher and higher powers of a fraction, you're just going to get increasingly close to 0, but never actually get there. The key thing then is this, when the b is greater than 1, is an example of exponential growth. And this is an example of exponential decay. And yeah, that is the basic overall shape. So quick couple of examples to show this. This is an exponential growth because the b is greater than 1. So this is, I'm going to say, expo growth. This would represent the y-intercept, so it's going to cross at 2. And then all I really want to depict past that is just a going up sharply to the right and then kind of leveling off to the left. That's all you really got to do. For this one, again, this will be the y-intercept, so it's crossing at 4. But this 0.5, that b is less than 1, but it's greater than 0. It's a fraction, so this will be an exponential decay. So it will be something that looks generally like this. And that's all I got to really depict, something like that. You could stop the video and try drawing these. I'm going to say right now, if ever you're having trouble with drawing these, feel free to use Desmos. It is a free online graphing calculator which is on the SAT, and a lot of times when people are drawing these, they don't draw the best pictures, and it's like, you should just check it on Desmos so you can learn from that. But in real brief, these should look like, I've got a leading coefficient of the implied 1 there, which means the y-intercept is sort of the default 1, and that base is greater than 1, so this is exponential growth. So just something like that. That's about a good depiction of the graph. Again, we technically have a horizontal asymptote right along the x-axis. This thing crosses at 3. So that's my y-intercept. But this, that's 1/2. That's exponential decay. So it looks something like this. And then this one's a little tricky. Okay, 1.5, that's your y-intercept, so somewhere about there-ish. 3.5, that's a decimal. So is it exponential decay? Well, no, all that matters is that 3.5. 3.5 is greater than 1. So it is exponential growth. Something like that. It's kind of hard to show this, but of course all of these have the same horizontal asymptote. They all level off, whether it be to the left or the right. They all level off at y equals 0.